Hello everyone, today's topic is testing of geotextiles. In geotextile part we have discussed the functions, the characteristics, applications. In addition to all these, testing and characterization of geotextile is extremely important, because the total structure, the performance of total structure, geotechnical structure or civil engineering structure depends on the characteristics of geotextiles. So, if we divide the test for geotextiles, we can divide it to two broad ways. So, first is index test, that is in isolation test, where we do not need any field trial, field test, or the textile material is tested separately in isolation. And if you want to know the performance characteristics, that is performance test is required. This performance test is carried out with the site specific soils and conditions. We should take the specific soil and we should create the particular condition during test, so that we can actually predict the performance of geotextile in use. The index test is simple, it is quick. On the other hand, the performance test, it is time consuming and it requires different setup. So, among the qualities or characteristics of geotextile, they are divided into three categories mainly. One is physical category, physical test, which deals about the physical characteristics of geotextile material, mechanical test and hydraulic test. Apart from this, there are endurance test and degradation test. So, endurance test, it is basically combination of mechanical and hydraulic characteristics, and degradation is mainly related to polymer characteristics. So, in terms of physical properties, they are mainly specific gravity, mass per unit area, thickness, stiffness. They are very important characteristics as far as geotextile is concerned. And specific gravity, if we see, it is defined as the material present per unit volume of, that is the material in unit volume. So, whatever material present per unit volume, and if we take the ratio with the density of the distilled water, so that we will get the specific gravity. It is measured using pycnometer method or density bottle method, where floating sinkers are used for testing materials. The typical value we see, if we compare, it is a rock, the density is 2.4, polyester it is ranging from 1.22 to 1.38, polypropylene 0.91. So, for designing geotextile we must know or we must measure the specific gravity. Then mass per unit area is very important. The tensile characteristics mainly correlate with the mass per unit area of material. So, here the materials are cut in a specific dimension and the material then is its weight, its mass is taken, and that when we divide the mass with the area, we will get the mass per unit area. While measuring the dimension, we should take precaution, it should not be stretched. So, we should cut the material without any tension. So, mass per unit area is total mass by total area, and cost of geotextile is normally it depends on the weight of, that is mass per unit area of geotextile. Thickness is basically it is given by the distance between upper and lower surface of the fabric. For textile material, we take the pressure 2 kPa pressure, because the material is normally it is a compressible material. Most of the geotextiles are compressible. So, we must specify the pressure. If we see the range of thickness, the oven or heat bonded non-ovens are thinner. So, oven geotextiles, the range of thickness is 0.25 to 1 millimeter, sometime it can go beyond 1 millimeter, and non-oven, if we see the thickness range from 1 millimeter to 10 millimeter and above, we can get very high thickness. This thickness is very important for the drainage and filtration application, and also we must know the compressibility of geotextile, because with the compression the flow characteristics also change. When we measure the thickness of geogrid or geomembrane, we try to keep higher pressure, that is 20 kPa pressure is used, that is the standard. So, this geotextiles, as I have mentioned, these are compressible. So, we must measure at certain pressure, that is 2 kPa. For compressible geotextile, we measure the thickness at 2 kPa pressure. Next coming the important characteristics for geotextiles, it is a stiffness. Stiffness, as we know, for apparel fabric, the stiffness is important for the comfort characteristics, tactile comfort, or for home furnishing, mainly it is related with the drape. But for geotextile, stiffness is extremely important for application with the different types of soil. Now, the measurement techniques of stiffness is similar to that of apparel textile. Here the stiffness tester like Surley stiffness tester can be used. The length, overhanging length, which is making 41.5 degree angle, that overhanging length is taken as stiffness. So, higher this length, higher will be the stiffness. So, 25 millimeter, approximately 1 inch wide strip is made to incline at an angle of 41.5 degree, and that length is measured, and the stiffness value is calculated by this formula, that is stiffness in milligram centimeter is equal to L by 2, L is the overhanging length by 2 cube multiplied by mass per unit area. That is the stiffness equation. So, we can get the stiffness value. Now, how this stiffness value is important for geotextile? Now, let us assume there are two types of soil. This is soil 1, very soft soil, and here another soil which is hard soil. Now, these two soils, for these two soils we have to lay geotextiles. Here geotextile is laid for the separation purpose. Suppose this is stone, these are the stones. Now, here I am putting geotextile. So, this is suppose this is geotextile, and here we are putting geotextile. Now, before selecting geotextile, we must know the characteristics of soil. This soil being very soft, they will get deformed easily. The geotextile will get deformed very easily by applied pressure, but here the soil is hard, the deformation will be less or negligible deformation. Now, if you want to use geotextile with the soft soil, in that case we have to select geotextile with a higher stiffness value, so that this deformation is not that high. Ultimately, this structure will remain intact. On the other hand, if we use here with the soft soil, if we use the flexible geotextile with a lower stiffness, then the structure may get distorted. So, that is why the stiffness selection is extremely important for geotextile application. Here if we say this table, the subgrade CBR, California bearing ratio, this California bearing ratio is one parameter that I will discuss in detail. This is the parameter which shows the stiffness of the or compressibility of the soil. Higher this value, the stiffer will be or the harder will be the soil. So, if it is very soft, the value is less than 0.5, in that case we need the geotextile with very high stiffness, say 15,000 to 25,000 is selected for the subgrade soil with CBR value less than 0.5. But on the other hand, if we use the hard subsoil, in that case like more than 2, in that case we can have geotextile with lower stiffness like around 1000 milligram centimeter. So, this way we have to select the stiffness. So, for soft subgrade we always select the stiffer geotextile. For example, the heat bonded non-woven fabric we may use, or sometime we use in combination. The property is important in field workability requirement, as I have already discussed for installation of geotextiles. If the soil is very poor or California bearing ratio CBR is very low, in that case we need stiffer geotextiles. Now, coming to mechanical properties, there are large number of properties we can test: tensile strength, fatigue strength, seam strength, burst strength, impact strength, tear strength, compressibility, frictional behavior, puncture test, pull out test, direct shear test. These are the tests we must perform to get the characters, to get a clear picture about the performance of geotextiles. So, we will discuss one by one. So, as far as tensile strength is concerned, here it is not like the apparel tensile characteristics. In apparel fabric we use the strip test, where the width of the strip is very low, but in geotextile this strip test result will not actually simulate the actual field condition. In actual application, in field application, we need wide width tensile testing as per as ASTM D4595 or ISO 10319 system. So, the width is very wide. We can perform graph test to simulate actual condition. Narrow strip test for only comparison, but it will not simulate the actual condition. Sewn seam strength of geotextiles can be done, because actually geotextile, the size we get, it is less than actual application. For that we need to stitch. So, the stitch strength we should get. Trapezoidal tear strength is required, because in case of any puncture, this actually puncture should not propagate. So, wide width test, here sample width is 20 centimeter and length is 10 centimeter. In case of woven fabric, we have to test both in warp and wave direction. So, machine strain rate is specified as per standard, it is 10 plus minus 3% per minute. The reason for selecting the wide width sample is that geotextile, particularly non-woven, achieve high Poisson's ratio from narrow strip. So, that will not give actual result. So, to reduce the Poisson's ratio, so we perform the wide width test, that is sample is mounted centrally and tensile strength is measured in terms of kilonewton per meter. So, per unit width we get the tensile strength value. In the strip test for apparel, we do not get in this form, normally we get in terms of gram per text or centinewton per text format. This is the text, the diagram shows the dimensions, 200 millimeter and 10 millimeter. For very wide width, the dimension is, the width is 1 meter and the length is half of the width. So, this is sometime recommended for geotextile application. Narrow strip we can test for just getting the idea, the index value we can get. The tensile strength appears to be less than the wide width tensile strength. As I have already mentioned, this test is not recommended for geotextile design, only for getting the idea about the tensile characteristics. As I have already mentioned earlier, along with the tensile strength value, we must get the total stress strain curve. So, from there we can get idea about the performance at lower strain. Now, for example, if we take the heat bond non-woven and needle punched non-woven, there if we see the needle punched non-woven is having higher breaking strength than heat bond, but at lower strain the heat bond non-woven is stiffer. So, accordingly, depending on our requirement, we can select. For that we need to have total stress strain curve. Now, graph test. As far as geotextile is concerned, the graph test is extremely important. This is for construction survivability test. Tensile test gives idea about the mechanical characteristics, but graph test, most of the condition, the geotextiles are subjected to graph test like situation. In graph test, the geotextile material, the sample is not gripped throughout the width, it is gripped at center. This situation normally occurs during application. Now, here if we see, it shows 3 stones of certain dimension and it is placed over geotextiles, and beneath the geotextile there are soft soil, and here geotextile is acting as separation and reinforcement purpose. Once the load is applied on this top stone, now I will show here. Now, here this is say geotextile is placed. This is geotextile. Below that there are soft soil. And above the geotextile, say this is one stone, another stone, this gravels are there. Now, once load is being applied on this stone, due to the downward force, these two stones will try to move sideways, and due to the contact point and at this point of geotextile, geotextile will be pulled. So, these zones are not being pulled. This is creating one situation this is geotextile, and here there is a groove. So, 1, 2, 3, this is groove second groove at this point, and this is third, and they are trying to pull side. The similar situation which is actually created here, like the has been tested in graph test. So, graph test is important characteristics, and as I have mentioned, it is specially for separation application in pavement. So, 25 millimeter narrow wide grip is there, loading rate is that is the strain rate 300 millimeter per minute. Non-woven geotextiles, the effects are more than woven geotextiles. So, it is expressed in kilonewton. So, as the sample is partially clamped, the stress is not propagated in the entire specimen, and which is actually simulating the actual condition. So, this is the diagram, these are the diagrams. The graph tensile strength is required to design the geotextile for separation application. When pressure is applied to the upper stone, it spreads the two lower stones laterally, it is trying to spread. As a result, tension is mobilized on the geotextile, and it is just analogous to graph tensile strength. So, these are the grips in dark blue color, and this is the specimen. Now, as far as Giroud, he has proposed one empirical equation. We can get the graph test by this empirical equation. So, if we see the diameter of stone D, let us see it is a average diameter, all the stones are having this diameter, and here this is the diameter D, and it is assumed that the space between the lower two stones are D by 2. So, total area here, total area it is a D by 2, and the total length initial length is that this D by 2, D by 2 and D by 2, this is the from this point to this point. Okay. So, this is the total initial length is 3 D by 2, and final length D, this is D, it has come inside D, and D by 2 and D by 2. So, this is L1 and this one is L2. So, if we take the strain, in this case the strain is 33% or 1 by 3, 0.33 is the strain, and T required is AP is the applied pressure from the top. We know the, if we know the applied pressure, and maximum void diameter, this void diameter, maximum void diameter for the stone system with the diameter D is 0.33 and dA is the average stone diameter. So, this equation can be used to calculate the required grab strength. So, if we know the required grab strength from all this data, and if we know the actual grab strength of textile material, we can calculate the factor of safety. So, this is a simple problem. The tire inflation pressure, which is actually the applied pressure, it is 450 kilopascal. The average stone diameter is 30 millimeter. Assume the geotextile is placed beneath the stone base course, that is stone base course is there. Calculate the required grab tensile strength of geotextiles. So, we have to calculate the T required grab strength. Here assumption is that 60% of the total ultimate grab strain is being utilized. So, here in this condition we have not considered any slippage. So, 60% strain is being used means there is 40% slippage took place during this sliding. So, if we assume that the grip is proper, there is no sliding, then it will be 0.33. If 60% is being used, that means actual mobilized grab strain is 0.6 multiplied by 0.33. So, 0.33 is, that is 1 by 3 that strain. So, that strain multiplied by 0.6. So, 0.198 is the actual strain of geotextile. So, we know this pressure, and here it is a 30 millimeter diameter. 30 millimeter diameter means 0.03 meter, the unit is in meter. 0.03 meter is the diameter of the stone, average diameter, and if we go back to earlier slide, the dV is the maximum void diameter, which is 0.33 into average diameter. So, this dV, so 0.33 into average diameter square multiplied by 0.198. So, the required grab strength here is 8.73. So, if we want say factor of safety of say 4 or 5, so if we want factor of safety of 5, so we must have one material geotextile whose grab strength will be 8.73 multiplied by 5. So, typically we try to keep higher factor of safety in geotextile application, because they are for protecting the structure. Trapezoidal tear strength, here it is tested to ascertain construction survivability. In case of any puncture, how quickly that puncture will propagate, that is tested. So, initially small cut is given in the sample, and the force required to propagate the tear in the sample is measured. The force is applied on the sample in such a way that initial tear is open up. So, there is a initial tear is created, and result is in Newton, expressed in Newton. So, the tear strength is important when geotextile is damaged. So, during laying up or during use, there will be some portions which are damaged, and we need higher tear strength, so that it can prevent the propagation. This is the sample size as per ASTM. So, 200 millimeter length, this is 100, this is the grip line, and here the cut is made, and we measure the strength required to propagate this cut. So, normal size roll width is 3 to 5 millimeter. So, now we can discuss the Sewn seam strength of geotextile. So, larger area has to be covered. So, we need to have stitching. There are different types of stitches: single stitch, double stitch, J seam, butterfly seam, there are commonly used, and tensile strength of normal portion and tensile strength of stitched portion is measured, and the ratio of strength at seam and strength at the virgin material is calculated as percent, and which is seam efficiency. So, seam strength efficiency is that the T seam and T strength of geotextile without seam. So, that ratio. Now, coming to another characteristics, that is compressibility, which is very important as far as the geotextile drainage and filtration application, which indicates, that is compressibly indicates the reduction in thickness under pressure. And as we have discussed earlier, that non-woven, particularly needle punched non-woven, the compressibility is very high. Due to higher compressibility, when load is applied, their transmission characteristics gets reduced, and the permeability property are dependent on normal pressure. So, higher normal pressure means that the structure will get compressed and permeability and transmissibility gets reduced, and compressibility of woven and non-woven heat bonded geotextile is low, whereas for needle punch it is very high. Next characteristics is the puncture resistance. Here the puncture resistance is measured by 8 millimeter diameter probe. This is 8 millimeter the diameter probe, and the container diameter is 45 millimeter. This is a 45 millimeter. Here this is the geotextile material, and before, just before at the time of punching, the peak load is measured and it is expressed in terms of Newton, and this puncher actually moves at a certain specified speed. Next punching test is done by CBR puncture test. This CBR test, California bearing ratio test, as it is basically for the soil particles, it measures the compressibility of soil, but using this technique we can measure the puncture strength also. It is similar to earlier test, that puncture resistance test, where probe diameter was 8 millimeter, but in CBR test the standard probe diameter is 50 millimeter. In earlier case container diameter was 45 millimeter, here container diameter is 150 millimeter. So, the 10 normally standard 10 specimens are taken, average is reported here, and using this value, puncture resistance value, we can also calculate the tensile strength, like wide width tensile strength can be predicted using this CBR puncture data. So, this is the value TF is the wide width tensile strength in terms of kilonewton per meter. This is the puncture force is in kilonewton. If we know the force and if we can calculate the circumference of the puncture, that is the 2 pi r, r is the radius of CBR puncture, here radius is 25 millimeter, this puncture radius, and this are the circumference is the total width if we talk about the tensile testing. So, that is why it is calculated Fp divided by 2 pi r. Here we get the idea about the tensile strength, and also we can get idea about the tensile strain, where A is the initial length of the specimen, that is the initial length, that means the radius of the specimen, and here this inclined length, this is the the strained length extended length, which is x. So, by this ratio we can calculate the strain value. So, using the CBR puncture test we can also get idea about the tensile strength and tensile strain. Now, coming to actual CBR testing, California bearing ratio test for soil particles. It is a penetration test for evaluation of mechanical strength of road subgrade and base course. So, road subgrade strength, compressive strength we must know. It is developed by California Department of Transportation, that is why the name is California bearing ratio. The test is performed by measuring the pressure required to penetrate a soil sample with a plunger of standard area. The measured pressure is then divided by the pressure required to achieve an equal penetration on a standard crust rock material. So, this standard crust rock material is basically which is very hard, and if we compare the pressure required with the actual specimen, then we will get the one ratio that is called California bearing ratio. Here if we see that for a given soil we have got a data, this data 0.025 inch penetration. For that penetration we need to apply 70 psi, pounds per square inch, and gradually if we want to penetrate this plunger at higher distance, we need to apply higher pressure. Typically 0.1 inch and 0.2 inch, these two data are taken. The pressure required to penetrate 0.1 inch and pressure required to penetrate 0.2 inch is taken to calculate the California bearing ratio. This is the plot we get, that is the penetration and the load value, or we can get the pressure value. This from this data, this is the plot, and from this data we can calculate the CBR value. So, let us take 0.1, here it is 0.1 is coming, it is a 220 psi, 0.2 here it is a 300 psi, 0.2 inch, and for standard value is that for gold standard CBR is 0.1 inch. This is the standard material for the test in crust California limestone. This is the crust California limestone. This is the standard value. For 0.1 inch penetration we need 1000 psi, or for 0.2 inch penetration we need 1500 psi. Now, if we get the ratio between say 0.1, if we take in 0.1 inch penetration 220 divided by 1000 multiplied by 100. So, that is the percentage, that is the actually called California bearing ratio, and if we want to calculate at 0.2 penetration, so that will be 300 divided by 1500. So, in this way if we see for 0.1 penetration we are getting 22% is the CBR value. So, or directly we can normally we express 22, and 0.2 penetration we get 20%. So, in among 0.1 and 0.2 we try to get the CBR value which is higher, that is the standard value. So, for this example the CBR of the material is 22%. So, accordingly if we know the CBR value we will get idea about the compactness of the soil or compressibility of the soil. So, if we get the try to see the standard value CBR value, the harder the surface the higher is the CBR value. A CBR of 3 equates to tilled farmland, very weak farmland, the CBR is 3, and moist clay it is 4.5, and high quality crust rock CBR is 80, like that, and California limestone which is definitely 100. So, as this is the reference value, and accordingly we can calculate the CBR value. So, higher the CBR value, the stronger that is the rock or this surface will be very hard. Another parameter which is important is a dynamic puncture strength. This type of situation can occur during laying of geotextiles. So, where the 1 kg pointed cone is dropped freely on geotextile, and the length of penetration we can calculate. So, here it is gauged at different height, it is gauged, and the diameter we know at different height the diameter will be different. So, diameter of the hole made by the cone is measured by graduated cone. This is the graduated cone, we can directly measure the what is the diameter of the hole. So, larger the hole, lower is the puncture strength, we will get direct idea. Then another mechanical characteristics which is Mullen the bursting strength. There are 3 types: Mullen bursting strength, ball bursting strength, and CBR bursting strength. This CBR testing it is used for puncture resistance also, and here we can use as bursting data. So, in Mullen bursting strength where the diaphragm is used, and ball bursting strength here one puncture will be used with the ball at the tip, and CBR bursting strength is here one plunger with it is a cylindrical plunger is used. In most of the applications it is actually this type of Mullen bursting strength is used. So, burst strength is required to design geotextile for separation. Again the geotextile may burst due to the applied upward pressure. Now, here these are the stones. Okay. Now, here it is used as separating material, that geotextile is used for separator, and at the bottom there are soft soils. So, this separation function is that this geotextile is actually not allowing this soft soil to penetrate inside, but once the pressure is applied, this soft soil will be pumped, try to be pumped inside, and this type of situation will occur. So, this soil will try to penetrate inside. So, here the bursting situation is created. So, field model for burst resistance, this is the picture here, geotextile being forced up by pressure Pg, this is the Pg pressure geotextile into void of stone due to this is a base soil. Okay. There is a stone, that is why it is pumped inside, and mainly bursting pressure is created in this zone. So, this Mullen burst test it is analogous to the field condition like stone punching into the separation layer, that is I have explained. The inflated rubber is of certain diameter, the hemispherical condition is created, and here as geotextile is pushed inside. So, we can calculate the ultimate strength. This is the ultimate strength of the geotextile, that is tensile strength, and that can be related with the bursting strength by this empirical formula. It is half Pb, which is the bursting strength, dB is the diameter of burst equipment, this is the diameter of burst equipment, and Eg is the strain in geotextile. So, if we know the strain in geotextile and diameter and bursting strength, so that we can predict the tensile strength, or on the other hand if we know the tensile strength and diameter and allowable elongation or elongation taking place in geotextile, we can calculate the bursting pressure. Next mechanical characteristics is that which I have already explained. I am not going to explain here in detail. So, mechanical characteristics is the mechanical interaction, the shear stress is developed, shear strength is calculated against the soil. So, it is done by pull out test and direct shear strength test. So, here the geotextile is confined in between the soil in both the sides. So, it then pulling force is applied, and depending on the frictional interaction the pulling force will change. So, from this pulling force we can calculate the interaction between the geotextile and soil. Another method is that it is a direct shear test, where this is the base soil and top soil is there, and on the base soil there are two blocks. On the lower block geotextile is covered with the geotextile, and then top soil it is actually slided, it is sheared against the geotextile, and we can calculate the shearing force. And next characteristics are hydraulic properties, and that I will discuss in next class. Till then, thank you.